I am Dr. Asima Saikia from Department of Geology, University of Delhi. I will take up the module on crystallography and will discuss about external symmetry. As an outcome of this module, we would like the students to learn about what is crystallography, how to define a crystal, the different forms of crystal, and the geometric relationships which defines the symmetries in a crystal. We will discuss in detail about all these aspects in our classroom. Crystals, when develop euhedral forms, they reveal symmetry. Symmetry is nothing but a geometric operation which helps us to understand the different geometric movements which can operate within the internal structure of a crystal, like the reflection, we have the which is the mirror plane, then we have axis of rotation, then we have inversion, and then we have translation. Crystallography, which is a branch of mineralogy, deals with the external form of a crystal, its intracrystalline internal structure, and the principles which govern their growth, shape, and occurrence in a particular geologic environment. So, in our class today, we will discuss what is first a crystal. A crystal is nothing but a three-dimensional repetition of atoms, ions, or molecules with a fixed interatomic distance, and each has as such no origin as they are repeated in space. So, to understand a crystal, there are laws of crystallography, and the first law is the law of constancy of interfacial angle, and this is what is called as the Stano's law of constancy of interfacial angle. So, the first thing which comes to our mind is what is an interfacial angle. So, interfacial angle is nothing but, say for instance, we have a crystal form where we have a crystal face which is triangular in shape, for instance, and any normal drawn on the crystal face from on this face and also on this face, and the angle which is subtended by this is the interfacial angle. So, this law states that for all the equivalent faces of a crystal, if the interfacials are measured at angles are measured at the same temperature, it will be always equal. So, for instance, if I have a quartz crystal which is manifesting two different geometric forms, for instance, one is something like this, and say the other one is something like this. Any cross section of these crystal, or for that matter this crystal, for instance, if it subtends a face like this, and for this crystal, for instance, it subtends a face like this, the angle here, here and here all will be, say for instance, if it is 120 degree, it will all be 120 degree, and for here as well it will be all 120 degree. And this is what is the law of constancy of interfacial angle, that for a particular crystal of a particular mineral, the interfacial angle will always remain the same if it is measured at the same temperature. Then we have the law of, so how do we measure an interfacial angle? For that we have a equipment called as contact goniometer. Which is nothing but a protractor. We have this D, and attached with it we have a plastic flap. So, how do we measure it? We will make this plastic flap lie on one crystal face, then the D will be adjusted against another crystal face, then the angle between these two, which is these two are normals to the crystal faces, and the angle alpha, which is also known as the internal angle, is what is the interfacial angle. For instance, if alpha is 40 degree, then there is also another term called as external angle, which is nothing but 180 degree minus 40, and which will be 140 degree. So here this is the internal angle, and here also you will see that these angles of standard will also be equal to alpha, and these both angle will in this case will be 40 degree and 40 degree. So this is our way of measuring the interfacial angle. Then we have the second law, which is the law of rational indices. Law of rational indices. Herein we have two concepts. One is the parameter and one is the indices, or commonly called as Miller indices, after the scientist who found it out. So here we have, say for instance, we have three crystallographic axes, X, Y, and Z. And we have two crystal faces. For instance, the first one is this. This is the O, the origin. We have A, B, and C. Then we have another crystal face which is like D, E, and F. The parameter for the face ABC is nothing but the intercept of the crystal face on the crystallographic axis X, Y, and Z. So for that matter, for the ABC face, we have the parameter as OA is to OB is to OC. For the face DEF, we can consider the ABC face to be the standard for that, and we can write that OD is nothing but equal to OA, OF is twice of OC, and OE is half of OB. So the parameter for this face will be OD is to OF is to OE equal to OA is to twice OC is to half OB. So that is 1 by 1 is to 2 by 1 is to half. So that is, we have 2 is to 1 is to 1, which is the parameter for this crystal face DEF. Yeah, if moving on to how to arrive Miller indices. Miller indices is nothing but the reciprocal of the intercept of the crystal faces. For instance, a face has a crystallographic intercept of 1A is to 2B is to 1C. Here A, B, C are the crystallographic axis. We will invert this. So it is 1 is to 1 is to 1 is to half is to 1 is to 1, which will have 2, 1, 2. This we will represent in second bracket, which is what is given as Miller indices of a face which has an intercept of 1 unit distance in the A unit direction, crystallographic direction, 2, it intercepts the B axis at 2 unit distance, and it intercepts the C axis at 1 unit distance. So this is what is the Miller indices for such a face. So the law of rational indices is nothing but it states that the ratio of the intercepts and its inverted values are what we have as the Miller indices, and this is what is the law of rational indices. Apart from these two laws, we have three more laws of crystallography. One is the law of constancy of axial ratio, law of crystallographic axis, law of constancy of crystallographic symmetries. These three laws basically try to say, law of axial ratio tries to say that for a given mineral, the axial ratios of the different crystal forms acquired by that mineral will always remain constant. Then for the law of crystallographic axis, it says that a variety of mineral or crystal forms which can be acquired by a mineral will have the same axis of symmetry, and the law of symmetry of crystals indicates that the minerals crystallizing or the crystals crystallizing under a particular mineral group will all have the same set of symmetries. So, when we have understood about these laws, now we can move on to what is a crystallographic axis and how it is assigned in different manners to different crystallographic systems. So, in the beginning itself, I have explained that when we describe a crystal, there are three aspects to it. First one is the geometric aspect, which we are dealing with in crystallography. The second aspect is that of the crystal chemistry of that is the chemical constituents which constitute that crystal, and the third is about its physical properties like its hardness, its brittleness, its magnetic properties and so on. So, to explain the geometry of a crystal, we need to define the three-dimensional object crystal in space. Basically, the crystallographic axes are adopted to define that. So, we basically assign a coordinate system. For instance, for the simplicity of matter, we can start off with three crystallographic axes, which can be x, y and z, which are all of equal length and are subtending an angle of 90 degree to each other. So, basically in crystallography, instead of x, y and z, which is the Cartesian coordinate system, we adopt a system which is called as A, B and C crystallographic system. Actually, there we have a three-dimensional object, so we have a negative coordinate as well. Here is A is positive, here B is positive, here C is positive, we have C negative here, we have A negative here, and we have B negative here. And the angle between B and C is alpha angle, between C and A is beta angle, and between A and B is the gamma angle. Based on these parameters, there are 6 crystal systems which are assigned. For instance, we have the isometric system, which is when the A crystallographic axis is equal to B crystallographic axis and is equal to the C crystallographic axis, and when the alpha equal to beta equal to gamma angle is equal to 90 degree. So, this is one set of crystallographic parameters which can be used to define a geometric shape of a crystal occurring in various crystal systems. So, we have likewise we have tetragonal system wherein A equal to B and is not equal to C and alpha beta gamma is 90 degree. Then we have orthorhombic system where we have A is not equal to B is not equal to C, but the alpha beta gamma is equal to 90 degree. For the hexagonal crystal system, we have 4 crystallographic axes wherein we assign the crystallographic axes as the ones. For the crystallographic axis in hexagonal system, I would like to draw this. We have 3 crystallographic axes A1, A2 and A3 all lying on this plane, and then we have the C crystallographic axis. So, there are 4 crystallographic axes in case of an hexagonal system, which is an aberration from the other crystallographic systems, and the details of this you can find it in the text where it is listed for each of the crystallographic system what will be the crystal parameter, that is the equivalence of the different crystallographic system in dimension, and also for the angle subtended by them between each other. Now, we will discuss about the symmetry elements which will help us to define the geometric operations which will help us to define the symmetry inherent in a crystal. So, we have three symmetry elements basically. We have symmetry with respect to a point, symmetry with respect to an axis, and symmetry with respect to a plane. So, I will explain the three symmetry elements first. So, first is symmetry with respect to a point. Here we have the crystallographic axis. Here we have a motif. Motif is nothing but is representative of the ion atom or molecular group which defines the unit of a crystal, and this is what is the motif. So, if I invert that from here, this is what is called as I, inversion center, and this is what is called as the symmetry with respect to a point. Then we have symmetry with respect to a plane, which is where we have the three crystallographic axes like this. We have A, B, and C. For instance, if I have a crystal motif here, I will have it inverted over here, provided I place a plane here which is called as mirror plane. I have simple reflection of this point on the other side and it is laterally inverted. Then we have symmetry with respect to an axis. So, it is nothing but when we have a symmetry like this, for instance, if I have this is my object, and if this is the point which I want to repeat, I can have either, if I want to get it back to the same position, I should have to rotate this by 360 degree, and this is what is called as one-fold axis of rotation. Basically, we will repeat the crystal faces by rotating it. We have two-fold axis of symmetry, we have three-fold axis of symmetry, we have four-fold, we have six-fold, and we have one-fold. One-fold is nothing but we repeat it by 360 degree. For two-fold, it is 360 degree divided by 2, that is we will have two rotations each of 180 degree. For three-fold, we will have a rotation of 120 degree each. For four-fold, we will have a rotation of 90 degree each, and for six-fold, we will have a rotation of 60 degree each. Apart from these three symmetry elements, we have another symmetry elements which is called as the roto-inversion. Herein we have nothing but we have a symmetry operation here. First we will rotate it, for instance, by two-fold axis which is 180 degree, and then I will invert it through the center and I will repeat it, reproduce it here, and this is what is the roto-inversion symmetry. So, we have in total 4 symmetry elements. With respect to an axis, we have two-fold, four-fold, six-fold, three-fold, and one-fold. We have axis of roto-inversion which is one-fold, two-fold, four-fold, three-fold, and six-fold. Then we have mirror plane which is designated by M. Then we have center of symmetry which is designated by I. Here in these point groups 1 bar, 2 bar, 4 bar, 3 bar, and 6 bar, these also have equivalent symmetry positions. For instance, 1 bar is equivalent to I, 2 bar is equivalent to M, 4 bar is unique, 3 bar is 3 plus I, and 6 bar is nothing but 3 by M. That is, we have a three-fold axis of symmetry. Perpendicular to this, we have a mirror plane. In case of three-fold axis of roto-inversion, it is nothing but the three-fold axis of symmetry with an inversion center associated with it. So, combination of these symmetry elements, which is also called as translational free symmetries, because there is no movement of point is associated in these kind of symmetry movements or symmetry operations. So, these are also called as translational free symmetry and also called as external symmetry, which is what we are dealing with in this module. So, combination of these external symmetry points lead us to derive 32 combinations which cannot be, which are not repetition of any of the combinations available. So, these 32 points or 32 combination of these symmetry elements is what we have as the 32 point groups. Point groups nothing but symmetry operations which can be passed through a center or passed through a point, common point, and that is what is we have the what is called as the point group symmetry. Point group symmetry is also assigned to the different crystal classes. For instance, in the isometric crystal system, we will commonly encounter point groups like 4 by m, 3 bar, 2 by m. For instance, in the tetragonal system, we will have 4, 3, 2, 4 by m, 2 by m, 2 by m. So, characteristic point groups are assigned to all the 6 crystallographic systems, and this is how we arrive at the what is called as the Harman-Muigam symbol. So, for each crystallographic system, a set of combination of point groups is what is defined as the Harman-Muigam symbol for that crystal class of that particular crystal system. Now, we will discuss about the crystal form. We had earlier discussed about morphology. Morphology is the external shape, but when we discuss about, we say about a form of a crystal, it is more on a restricted note, because form defines all these similar faces which can be linked together because of their similar symmetry elements. So, forms can be of two types. There are special forms and there are general forms. So, for each point group of the which defines the 32 crystal classes of the 6 crystallographic systems, we have 32 general forms. That is a crystal form which cuts the crystallographic axis of the concerned crystallographic system at different lengths, and rest all other forms of crystals are called as special forms. So, in total we have 32 forms for each 32 point group. Then we have 10 special forms for closed special forms of isometric system, and then I think we have another 6 special forms which are open crystal forms and which belongs to tetragonal and hexagonal system. Usually 2 methods of describing a form is adopted. We have the method by Groth and Rogers, and we have the method which is followed after the Fedorov Institute of Leningrad, which has defined this. So, mostly we can define 5 forms, mostly define all of the crystal forms which we see, for instance, prism, dipyramid, monohedron, prism and dihedron, and apart from that some special forms like scalenohedron, trapezohedron are there. So, all these are listed in the text which can be referred to, and we will in the next class discuss about how to arrive at the different point group systems mathematically, and we will discuss in detail how each point group is assigned to a particular crystallographic system based on its symmetry elements. Today from our lecture we have understood what is crystallography, which is a branch of geology which deals with the external form of a crystal and the geometric relationships which define the internal structure to understand a crystal better. We also got to know that a crystal, what is a crystal? We have also tried to understand the different laws which govern a crystal. For instance, Stano's law of constancy of interfacial angle, law of axial ratio, law of constancy of axial length, law of symmetry of planes, law of symmetry of lengths, and also we have understood the different symmetry elements. For instance, we have the symmetry with respect to an axis, symmetry with respect to an plane symmetry with respect to a point, then we have symmetry with respect to a point and also an inversion associated with it. And also we have tried to get to the point that what is a point group, and we now know that point groups are nothing but a combination of all the external symmetries. And we have also got to know the various geometrical forms a crystal can acquire from different crystal systems. Apart from this, we have also got to know that based on these symmetry elements, we can define the crystal systems into 6 classes which have distinct crystallographic axis lengths, and also we have different angles between these axis lengths, and that also helps us to assign the different point groups to the crystallographic axis crystal systems we have, and the forms can help us to identify them when we see them in field, and we hope to move on to derive these point systems in our next class.